bias, correlation, and tensor rank. Mrinal, whenever you're ready.
Thanks, Mary. Can you hear me?
I can.
Okay, great. And can you see my screen now?
Yep.
Okay. So let me know whenever, when to start.
It's 11:20, so why don't you go for it now?
Okay, thanks. All right, so I'm going to talk about multilinear forms, their bias, correlation bounds, and tensor rank. And this is joint work with Bshouty, Prahlad Harsha, Pooya Hatami, and Swastik Koparthi. This short talk is going to be about three of those things. So it's going to be about multilinear forms, bias, and tensor rank. I'm only going to mention correlation in passing at some point. All right, so let me start by defining D-linear forms. This is definition by example. So a bilinear form is a polynomial of this form. There are two sets of variables, x and y. So x1 up to xk, y1 up to yk. And a bilinear form is a polynomial which is linear in both x and y. So it's of the form sum over I comma j, t sub ij, xi yj. All right, and throughout this talk, so every polynomial that we are going to look at, the coefficients will come from the field F2. Right, so this is a polynomial. There's a natural matrix, natural k cross k matrix that you can associate with it. So the I comma jth entry of this matrix will be the scalar t sub ij. All right, a trilinear form will have three sets of variables, so x1 up to xk, y1 up to yk, and z1 up to zk. And it's going to be linear in all the three sets of variables. So it's going to be of the form sum over ijl, t sub ijl, xi, yj, zl. And all the tij's will again be from F2. And just like we could identify a matrix with a bilinear form, we can identify a three-dimensional tensor. So it's like a k cross k cross k cube with entries from F2 associated to the polynomial p, and the ijl entry of this tensor will be t sub ijl. All right, so what do I mean by rank of a D-linear form? By rank of a D-linear form, I mean the minimum R such that the form P can be written as a sum of R D-linear forms of rank 1. Okay, so what does that mean? So again, by example, so for a bilinear form, it means that you can write P as a sum of R terms, and each term is going to be of the form, so it's a product of a linear function in x and a linear function in y. So each L and M here are linear forms. All right, and this other view of a bilinear form that we had, the matrix associated with it, it's not hard to observe that the rank of the form P is precisely equal to the rank of the matrix T. Similarly, for a trilinear form, a rank just means that we want to write P of x, y, z as a sum of a bunch of terms, and each terms look like a product of linear function in x, in y, and in z. And this precisely corresponds to a standard notion of tensor rank of the corresponding tensor T. All right, so the problem we were interested in was the question of lower bounds on tensor rank. So we wanted explicit tensors with high rank. So we know that a random three-dimensional tensor, so a random k cross k tensor has rank about k squared. Right? We also know explicit families of tensors of k cross k tensors whose rank is k, but we don't know any superlinear bounds on these things. So we don't know explicit tensors with rank little omega k. In fact, this is one of those annoying problems where not only do we not know a tensor of this kind, we really have no idea of how to go about proving such things. And tensor rank low bounds, it's interesting on its own as a problem, but it also has some very, very nice consequences to algebraic circuit low bounds. The current best bounds for tensor rank over F2, so three-dimensional tensors over F2, is 3.52k. This is from the 80s, and so a bunch of papers proved it throughout the 80s. So Brown and Dobkin proved it the earliest, as far as I know. There was a follow-up paper of Chudnovsky, which had the same result, and then one by Sparlinsky, Spassman, and Vladul. And this continues to be the best bound more than 30 years later. All right, so before we get on to the results, I have to define what a bias means. Okay, so bias is a very, very crude measure of how balanced a function is. So what does this mean? So bias of a form P is just this expression, which if I rearrange, so it looks at the how often the function is 1, takes the value 1 in F2, and how often it takes the value 0, it takes the difference of these two. Right, and it's a very crude measure of pseudo-randomness in some sense, and it's not hard to show that for every D linear form, the bias is at least 2 to the minus k. And for this, for the notion of bias, if this was our measure of pseudo-randomness, we know explicit and very, very natural 3 linear forms which have minimum possible bias. All right, so let me state the results. So one of our results, we show a connection between bias and tensor rank. So again, P is the trilinear form, T is the corresponding tensor. So informally, what we show is that if the tensor rank of T is low, then the bias of P should be high. Or if I look at the other direction, it means that if P has low bias, then T has high tensor rank. All right, and why is this interesting? So P having low bias is something that we know how to do. So we know how to construct explicit P which have very low bias, and this gives us a possible route to construct tensors T which have non-trivially high tensor rank. Okay, so if I have to state it a bit formally, then what we show is that if the tensor rank of T is at most R, then the bias of P must be at least 3/4 to the R. Okay, so if we invoke this statement, so we know explicit construction of 3 linear forms with minimal bias, so bias about 2 to the minus k. And if we plug it into this expression, we get that the tensor rank of T is 2.4 times k. So remember, k was what we could prove otherwise. So 2.4 k is non-trivial. It's not super linear. It doesn't match the current best bounds, but it's non-trivial. But if we stare carefully into the proof and tighten some inequalities, use the fact that we are working with P with minimal bias, then we actually manage to recover the lower bound of 3.52k that we knew before. Like I said, this matches the best bound we know for any 3-dimensional tensor over F2. All right, so we have a few other results. So somewhere in the paper, we also prove correlation bounds for a random D linear form with lower degree polynomials. And in the process, we prove concentration bounds on the bias of a random D linear form. And this gives us nearly tight correlation bounds between a random D linear form with lower degree polynomials. This connection between bias and tensor rank also lets us prove a non-trivial low bound on the rank of the matrix multiplication tensor. This bound is not as good as the best bounds for this problem, but it's non-trivial. And yeah, that's it. So.
Thanks. So we have time for maybe just one super quick question. If anyone has a question, you can either ask in the chat box or just unmute yourself and ask.
So I have a question. What is that 3.5 to some ratio or something? Where does it come from?
So 3.52k in both the cases, in the case of the earlier results in our result, it comes from rate distance trade-offs for codes over F2.
I see. Thank you.
Okay, so I think in the interest of time, it's best to move on to the next talk, but thanks again, Mrinal.
Thanks, Mary.
Yeah, so for the next talk, Anurag, are you giving the talk?
Yes.
Okay, yeah, so our next speaker is Anurag Pandey, who's going to talk about polynomial identity testing for low-degree polynomials with optimal randomness. So yeah, go ahead.
Thanks a lot for the introduction. So I'll be talking about polynomial identity testing, and this is based on a joint work with my advisor, Professor Markus Blaser. Let's get started. So in the polynomial identity testing problem, or the PIT, we are given a multivariate polynomial, and we have to decide if it's an identically zero polynomial. Yeah, an identically zero polynomial is a polynomial whose all the coefficients are zero. For instance, if we are given this polynomial, x plus y whole square minus x square minus 2xy minus y square, then this is an identically zero polynomial. On the other hand, if we are given this polynomial x square minus x over the field f2, then even though it evaluates to 0 on both the field point, we say that it is not an identically zero polynomial. Yeah. So PIT is quite fundamental both from the perspective of algorithm design and complexity theory. For instance, testing perfect matching in graphs and primality testing, they reduce to PIT. And PIT is also known to be intimately connected to proving lower bounds via this hardness versus randomness paradigm. And also it has served as one of the flagship problem to understand the BPP versus P question. Yeah. So based on how exactly the polynomial is given, there are several variants of PIT. And the most notorious one among them is the so-called black box PIT, in which we are given only the oracle access to the polynomial. That is, we can only query for the evaluations of the polynomial. And based on these query results, we need to decide whether the polynomial is concealing an identically zero polynomial, or is it concealing some non-zero polynomial from a promised class. Yeah? And that promised class could be, for instance, set of polynomials computable by small size arithmetic circuits, or it could be a set of n-variate degree D polynomials. Yeah, so for PIT, in all these versions, there's a simple randomized polynomial time algorithm, thanks to famous Schwarz-Sibyl-de Miller-Lipton lemma. And when the black box conceals an arbitrary and variate degree D polynomial, if we are in this setting, then it is known that randomness is essential for any polynomial time algorithm. Yeah, and in that regime, the challenge is to minimize the number of randomness needed. This is what we address in our work. Yeah, so the problem is to come up with a polytime algorithm against n-variate degree D polynomial over field f, and such that it succeeds with high probability. So one could ask, is there a lower bound on the number of random bits? And indeed, if we are in the low degree regime, and if we set epsilon to be some inverse polynomial, and we restrict number of queries to be polynomial, then it can be shown that lower bound is something like d log n plus little of d log n. And note that we are interested only in the low degree regime here, because in the high degree regime, already there are algorithms which deploy optimal random number of bits. And so in this low degree regime, there are many algorithms which achieve order d log n, but all of them are constant factor away from this information theoretic lower bound. And this is what we try to bridge. And we come up with an algorithm which uses the number of random bits, which is d log n plus little of d log n. So it differs from the information theoretic lower bound only in the lower order terms. And yeah, and it works for all fields of size at least d plus 1. So a few words about the algorithm. So our algorithm is almost the same as an algorithm given by Bshouty, who gave a polytime algorithm that uses a number of random bits, which is something like 2d log n, and it worked for all fields of size at least d plus 1. And one of the crucial steps in his algorithm was to reduce the problem to the univariate setting using this map x1 to xn goes to x to the b1 to x to the bn. And this b1 to bn, they satisfied this property that they found what is called as a Seddon set. And so a subset of natural numbers b1 to bn is called a Seddon set. Seddon b less than equal to d set if we take two multi-subsets of this set of cardinality at most d, then their sum of elements will be different. And this is particularly useful because this maps every multivariate monomial of degree at most t to a distinct univariate monomial. And in particular, it preserves the non-zeroness of the polynomial, which is what we need. And it can be shown that in his algorithm, the number of random bits is dictated by log of Bn, where Bn is the highest among B1 to Bn. And he used two constructions of Sedan sets. Only one of them is known to be polytime constructible. And in there, log of Bn was upper bounded by 2d log n, something like 2d log n. And this is where our algorithm differs, because we use a different construction of Sedan set, where it turns out that log of Pn is upper bounded by d log n, and this is also polytime constructible. Yeah. And this construction was inspired by a blog from Timothy's Gauss blog, where he describes a construction by Imre Raza, and that construction essentially scales up for our purposes. And this construction at its core is based on the fundamental theorem of arithmetic. And yeah, so essentially we take the algorithm of Bshouty, and instead of using his Sedan set, we plug in a different Sedan set, and that turns out to be solving the problem. So yeah, that's all. Thanks a lot for your attention.
Thanks. So we have several minutes or 3 minutes for questions. So if anybody has a question, please either put it in the chat box or just unmute yourself and ask.
Is it possible to describe the construction of the Sedan set in a short description?
Yeah. So let's say you collect first n primes. Yeah. And we know from fundamental theorem of arithmetic that if you take two distinct multi-subsets of it, then their product will be different. Yeah. But here we want that their sums should be different. Yeah. So this suggests what could be tried. And yeah, so you try the log of the primes. Yeah, so you try the log of the primes, but the problem is that they are not natural numbers, and so you need to make them integers somehow to make them work. And if you make them integers in a naive way by just taking ceiling, then many of these sums of elements of multi-subsets, they will start colliding. So then you need to spread them out sufficiently apart so that it works. And for that, like there is a simple application of mean value theorem, which I have it somewhere. Yeah, so there is a simple application of mean value theorem which tells you, which gives a lower bound on the difference of the multi-subset sum if you use log of the primes, and you just scale these numbers by this product of primes, which is what we get from this lower bound. And then, yeah, with some additional idea, this can just be made to work. Yeah.
Any other questions?
I have a question. So if you don't care about polytime constructible, so what is the best construction that is known?
I think still, like to the best of my knowledge, I do not know of a construction which does better than this construction. Because Bshouty used two construction, and one of them had upper bound of Bn, which was something like n plus order n to the square root to the d plus 1. I think this is still worse than what we have, but I do not know of anything which might be better than this. But yeah, to the best of my knowledge, what we have is the best.
Thank you.
Mm-hmm.
All right, so let's thank Anurag again. Thanks.
Mm-hmm.
And next up, who's next? Zayu, are you giving the talk?
Yes, I'm giving a talk.
Great. Okay, so next up, we have Zayu Go, who's going to talk about improved explicit hitting sets for ROABPs.
Yes.
So.
I'm trying to share my screen.
Yeah, take your time.
Yeah. Could you see it? No.
No.
Let's see. Okay. Could you see it now?
Yep.
Okay. So I'm going to talk about, thanks for the introduction, and I'm going to talk about improved explicit hitting sets for ROABPs or black box PIT for ROABPs. This is joint work with Rohit Gurjar from IIT Bombay. Okay, so we are interested in polynomial identity testing or PIT, which is a fundamental problem in de-randomization. Here we are given a multivariate polynomial, and we want to know whether or not it's zero. And we assume the polynomial is efficiently computable in some model. It could be an arithmetic formula or circuit, or arithmetic branching program, or determinant of some symbolic matrix. So in this talk, we focus on the read-once oblivious branching program as the model, or ROABPs. So PIT for ROABPs and related models has been studied extensively over the last decade. It can be seen as the algebraic version of the RL versus L problem. So here's the definition for an ROABP. An ROABP is a polynomial that can be written as a product for matrices like this, where beta and gamma are column vectors, and each phi is a R by R matrix with polynomial entries in the variable x pi I, where pi is the permutation of the index sets 1 through n, and we say permutation pi specifies the variable order, the input variable order for the ROABP. So we could either assume the variable order is known to the algorithm, or we could assume it's not known. In our paper, we assume the variable order is not known, which only makes the problem more difficult. Finally, R is said to be the width of the ROABP, if the size of the matrix is also. This is an example of ROABP. Here I list some of the most important results. Rather than Spielka gave the first white box polynomial time PIT algorithm for ROABP. It's called white box because the algorithm has the full access to the input ROABP. And on the other hand, we could also ask for a black box PIT algorithm. So black box PIT algorithm means that the algorithm is allowed to evaluate the polynomial at a set of points, but the set does not depend on the set of evaluation points does not depend on the input ROABP. And finding our black box polynomial time PIT algorithm is open. This is equivalent to designing a polynomial size explicit hitting set. We say a set where we say a set H is a hitting set if so H is a set of evaluation points, and we say it's a hitting set if for any non-zero polynomial computed by an ROABP, its value at least 1 point is non-zero. Although it's open to find the polynomial size explicit hitting set for ROABP, Forbes and Spielka show that how to construct quasi-polynomial size hitting sets for ROABPs in the case that the variable order is known, and the size of their hitting set is polynomial n to the log n. And this was later extended to the case that the variable order is unknown. So the status of this problem is similar to what we know in the Boolean world, because we know explicit PRGs that has the log n square sequence for branching programs, like a Nissan's generator, but we do not know explicit PRG with a logarithmic sequence. So to state our results, let me first explain the parameters. We have three parameters, n, r, and d, where n is the number of variables and r is the width of the RABP, and d is the individual degree bound for variables. So for simplicity, I'm also going to assume the characteristic of the field is 0 or large. And our first result is an improved construction, explicit construction of heating sets for our ABPs with a known variable order. And the size of our heating set is the polynomial in D and the super polynomial in NR, where the exponent is log n over log n minus log r. A similar bound was shown by Bshouty earlier, but only for known order RABPs. Also, their bounds depends super polynomially on the degree, while our bound depends polynomially on the degree. And when the width r is sub-polynomial in n, and the degree is polynomial in n, the heating set has size n to the little log n. If you translate into seed length, it means the seed length is little log n square. This is in contrast to what we know in the Boolean world, because it's a famous open problem to construct explicit pseudo-random generators or heating set generators of seed length little log n square for read-once branch programs, even if we assume the width of the read-once branch program is constant and the variable order is known. Our second result is explicit heating sets for more general family of polynomials than our ABPs. We consider polynomials that can be written as the sum of constantly many RABPs in possibly different variable orders. For simplicity, let's only look at the small variator regime, meaning that n is O log d. In this case, a recent paper by Bshouty and Saxena gave a construction of size polynomial in R2 log d, and we improve it to polynomial in d and R2 log d. Our last result is construction for more special RABPs, namely commutative RABPs, or more generally something called any order RABPs. And the previous best construction for these families of RABPs has size polynomial NDR to the log r, and we improve it to polynomial ND and R to the log r. So now the dependence on the number of variables n and the degree d is polynomial. Finally, all of these results assume the characteristic is 0 or large. For arbitrary characteristics, we also get results that improve the previous results, but they are not as good as what I give here for 0 or large characteristics. Okay, so we pull our results by combining ideas, analysis in previous papers with the following ideas. The first idea is merging multiple parts at each level of recursion. So one common technique used in on this problem is divide and conquer, first used by Nissan for read-once branch programs. Namely, if you want to construct a PRG or heating set, you first divide your branching program of our ABP into two halves, and you recursively construct the heating set for each half and then merge them. So the recursion tree is like a binary tree. And we replace the binary tree by k-nary tree, meaning that we merge k parts at each level. It turns out that if the width is small, it gives a better construction if you choose k to be super constant. And this idea is not new. It's already used by Forbes and Bshouty, but only for known order RABPs, and we are able to make it work for unknown order RABPs. And the second idea is low degree concentration using random shift, or you could call it a degree reduction. So we choose a random element alpha from the field, and then we replace each variable xi to xi plus alpha by xi plus alpha. And it can be shown that if alpha is random, then with hyperability, then the fi after the shifting has some property called low degree concentration, which is useful for constructing the heating sets. And this essentially allows us to reduce the degree d to r squared in our analysis, which is an improvement if d is much larger than r squared. However, this technique requires the characteristic to be 0 or large. And this is the reason our results are better when the characteristic is 0 or large. And the last idea is reducing the number of variables using hash functions, or you could call it length reduction. This technique applies only to our last results about any other REPPs. So previous constructions of heating sets for any other REPPs use a property called the low support concentration. And one crucial observation in this paper ASS13 is that in order to achieve low support concentration, it suffices to achieve it only in small subsets. So this means the low support concentration is a local property. If you can prove it locally, you can prove it globally. And we exploit the locality by using hash functions. Namely, we use the hash function from the pairwise independent hash function family to map the set of n variables to a set of few variables, poly-R variables, and then we achieve low support concentration in the target set. And then we show that when we go back, this implies low support concentration for the original set. Yes, so, and this allows us to reduce the number of variables n to polylog R. So finally, let me give you some open problems. The first problem, natural problem, is closing the gap between our results for in character 0 or large, and those for small positive characteristics. And secondly, it's a big open problem to construct polynomial-sized heating sets for RABPs. And this is open even in log-variate regime. So that's the end of the talk. Thank you.
Thanks. So in the interest of time and staying on schedule, maybe we can take any questions offline, so you can just privately chat Zayu or email him, I guess. But thanks for the very nice talk. And so next up, we have our final talk of this session. Roy, are you giving the talk?
Yeah, can you hear me?
I can, yeah. So next up, we have Roy Tell, who's going to tell us about hitting set generators for polynomials that vanish rarely.
Thank you so much. And can you see the screen? Can you see the other slides too?
I can see this screen, and yep, so many slides. Looks great.
Yeah, perfect. Okay, I must say that it's really fun to have 3 talks in a row about the same problem. And like the way I see it, all 3 talks refer to special cases of the PAT problem. So both Anurag's talk and Zayu's talk refer to certain special cases of the problem. Anurag's talk to the case where the field size is large, and Zayu's talk to the case where the polynomial is kind of a read-once branching program with certain parameters. And I'm going to present another special case of the PAT program, the PAT problem. And this talk, as you said, is called On Hitting Set Generators, which is equivalent to the PAT problem for polynomials that vanish rarely. And it's a joint work with Dean Doron from Stanford and with Amnon Tashma from Tel Aviv University. And the way that I want to market this special case of the PAT problem is that it has barely been considered before. It's relatively new, it's unexplored, and we're not even sure what answers we should expect. So let's go just a tad slowly. The setting is multivariate polynomials over a finite field. So we think of the number of inputs at n, which is the main complexity theoretic parameter in this setting. So n tends to infinity, this is the asymptotic parameter, and the field size and the degree might grow with it. And think about every setting that you care about. For example, small fields and large degree, GF2 and degree square root n. Or if you want, you can also think like in Anurag's talk about large fields and degree that is smaller than the field and the number of variables. And we're going to talk again about the low degree setting. So it's a low total degree. And the classical problem, which is the 3rd talk in a row, it's the PAT problem in the black box setting. So we want to construct a small subset of the domain f to the n, such that for every degree d polynomial, there exists some element in the small subset on which the polynomial is non-zero. So let's do a visualization. This is f to the n. This is the non-zero subset of a polynomial. There's a point to this, so hold on. This is the non-zero subset of a specific polynomial. These are all the non-zero subset of all the degree d polynomials, and we want to hit them all simultaneously, which is real fun. And we care about this from a complexity theoretic perspective. So we get a seed length, we get a seed of length L, and we want to generate the ith element, and we want to do it efficiently. And as already been mentioned, in the general case, especially for small fields, this is a fundamental problem with implications in de-randomization towards BPP equals P in lower bounds for circuits and for polynomials, and it's an algorithmic tool, etc., etc. This is an important problem. And as has already been mentioned, we know the correct answer non-explicitly, it's d log n, and algorithmically we are far away in the general case. So we saw several solutions for special cases, and for example, like over GF2, the best known heating set generator has seed length approximately 2 to the d times log n instead of d. So there's an exponential gap. And like, of course there is, we just said it's a fundamental problem, BPP equals P, circuit lower bounds, etc., etc. This is a hard problem. So what's the special case that I want to present in this talk? We're going to ask what happens if we only want to hit those degree D polynomials whose non-zero set is huge. These are polynomials that vanish very, very rarely. They have very few zeros. And it should be very easy. First of all, we only want to hit very dense sets of non-zeros instead of all sets of non-zeros. And secondly, there are simply fewer such polynomials. So before going into parameters, this is an intuitively easier problem. And we're going back to the visualization from before. So this is f to the n. And these are the non-zero sets of degree D polynomials that vanish rarely. So you can see that these are very, very dense sets. So instead of considering all degree D polynomials, we're only considering those degree D polynomials whose non-zero sets are very dense. And look, it's very easy to hit them all simultaneously. You can even shift the dot pretty much anywhere, and you'll hit them. Okay, so let's be formal. We fix a degree, and we fix a parameter epsilon that will quantify the rarely in vanish rarely. And our goal is to construct a heating set generator that hits all degree D polynomials such that the probability of a random input that the polynomial vanishes is at most epsilon. Like the implicit question here is, can we make further progress in this special case on top of what we already know for the general case of all degree D polynomials? And before going forward, we need to clarify one technical point, which is if you think of large fields, then you think that all polynomials already vanish rarely because of Schwarz-Zippel. It's true that low degree polynomials over large fields vanish rarely, period. But the 2 points that make this special case interesting are first that we will care about epsilon that is even smaller than that. A tiny epsilon should be very easy. And second of all, which is even more important, is that we care about the case where the degree is much larger than the field. For example, as we mentioned at the beginning, for example, the field is a binary field and the degree is square root n, in which case there are a lot of polynomials with small zeros, with small non-zero set, but we discard them. We only want to hit those degree D polynomials that vanish rarely. So what do we know? In the general case, we knew which answer to expect combinatorially, and we tried to get it explicitly. Here we don't know anything. Neither of the two questions now has an obvious answer, which is interesting. I mean, the first step is that, okay, you get the non-explicit answer very easily, then you move on and try to get it like explicitly by a construction. But no, we don't even know what's the combinatorial answer. So the two questions, and these are two open problems. We don't solve them in this work. We make progress, but we don't solve them. And these are relatively new questions. What's the best seed length as a function of d and of epsilon to hit all degree D polynomials that vanish with probability epsilon? And can you get it algorithmically? And I'm going to skip about the slide of why this is important. It's a special case of a super important problem, and it's a natural question by itself. And I'm going to skip several connections to well-studied problems, although you guessed that there will be many connections. This is a natural question about polynomials. For example, how many polynomials are there that vanish with probability epsilon? We don't know. Okay. Let me state this one slide with several interesting special cases of our results. So first, we construct a polynomial time heating set generator with non-trivial seed length for degree D polynomials that vanish with probability 2 to the minus d minus some small additive factor. So the extreme value in which the problem becomes trivial is when epsilon is 2 to the minus d. And when we are very close to this extreme value, we get something non-trivial. When we go further away, you know what, let me just do this with a visualization. This is the leftmost part here. When we close to the leftmost part here, which is trivial, we get a non-trivial polynomial time heating set. When we get further away here, we don't know what the answer is. And when we reach this part here, in which the vanishing probability is 2 to the minus something that's not a polynomial power of d, 2 to the minus polylog d, something like that, we get a lower bound saying that the problem does not become easier. So in a sense, and I'm not going to go into parameters in a 10-minute talk, we focus on the very extreme range of parameters. We show that this is the only part in which things might be easier, and we show that things can be easier. We construct a polytime heating set generator in like settings in which in the general case we don't know of any such thing. That's it. Thank you very much for tuning in.
Thanks.
Thank you.
So maybe we have time for one quick question. So if you have a question, you can either type it in the chat box or just unmute yourself and ask. So I guess I have one quick question. So then you're saying your techniques sort of are focused on this very extreme end of this picture that you were drawing. Do you think that these same techniques could be used to sort of push it that way, or will fundamentally new techniques be needed, do you think?
I think the main theorem in the paper actually shows that once you reach, for example, this part, oh, you can see the small hand, right?
Yeah.
Okay, once you reach this part, like solving the special case of polynomials that vanish trivially is just as hard as solving the general case.
Okay, I got it.
At least in terms of seed length, maybe you can get a better explicit construction, but like the first step is understanding the seed length.
I see.
So we don't, and the explicit construction that we get is not something that will extend to this range. I think the main message to take here isn't that the techniques that we introduce already apply to the general case. It's that even for this special case, we don't know what the answers are, and it's been unexplored so far.
Cool. Thanks.
Thank you.
Cool. Okay, so with that, let's thank Roy again.
Thank you very much.
And let's thank everybody from this session and indeed all of today. So I guess that's the end of today's program for Random. So we'll see you all back here tomorrow for even more talks.
Let's also thank Mary for chairing the session.
and let's thank Raghu for chairing.
All right.
All right, so thanks everyone, and see you all tomorrow.
Okay.